This is the solution to homework set number 5 for ECE 321, Analog Electronics. The first problem is analysis of the DC operating point of a transistor amplifier. The trick with DC analysis is to replace the R1, R2, 300K, 700K with their Thevenin equivalent. The Thevenin voltage is by voltage division 300 over 300 plus 700 times 12, 3.6 volts. The Thevenin resistance at this point looking left is 300K in parallel with 700K, 210K. Now between the base and emitter I've got a diode. Emitter goes to ground through 1K, emitter is tied to collector through beta IB, and collector is tied to 12 volts through 3K. So here's the circuit that you analyze. This is the one that you build. To analyze it, the base current is, to my loop equation, minus 3.6 plus IB RB plus 0.7 plus RE times IB plus IC equals 0. Solving, the base current is the 3.6 minus 0.7 volts in the numerator. The resistance is 210K plus 1 plus beta times RE. That's IB plus IC. IC is beta IB. Gives you 7 microamps. Times 200, IC is 1.4 milliamps. Then the Q point, BCE, is the 12 minus RC IC minus RE times 1 plus beta IB. Gives you 6.348 volts. So there's your Q point. That's analysis of the circuit. Design is just go backwards. If I want the Q point to be 6 volts, what I do is redraw the circuit. This is R1 parallel with R2. There's your B Thevenin. If the Q point is supposed to be 6 volts, I can solve for IC. That's 12 volts plus IC RC plus 6 plus RE times IC plus IB equals 0. Gives you IC is 1.498 milliamps. IB then is 7.4 microamps. I now have one equation, two unknowns. VB and RB set the current. To stabilize the Q point, I pick RB to be much, much smaller than 1 plus beta RE. This is 201K, so pick RB to be much, much smaller than 201K. It just shows 20K, 10K, or 10 times smaller is the typical number. I now have one equation, one unknown. Pick VB to set the current, and that gives you VB is 2.35 volts. To find R1, R2 then, R1 in parallel with R2 is 20K. R2 over R1 plus R2 times 12 is 2.35 volts. Gives you two equations, two unknowns, solve, and you get 101K and 24K. That's design. Problem 3 is to analyze the circuit, find the small signal model for the common emitter amplifier. To draw it, I start at the input, assuming capacitors are large, meaning this is a negligible resistance. I then see R2 to ground, R1 to ground. Again, this is AC analysis. The 12 volt source is actually 12 plus 0 sine omega t. Since this is AC analysis, what we care about is that 0 sine omega t is 0 volts AC. So R1 goes to ground. Takes you to the base. Base goes to emitter, which is shorted to ground through a CE, through a diode, which is modeled by a resistor RF. Emitter is tied to collector through beta IB, and collector is tied to ground through 3K. So there's a small signal model. RF is 0.052 over the base current that we calculated from problem 2, 6942 ohms. Now to find the two-port parameters. Looking in, I just see R1 in parallel with R2 and parallel with RF, 5154 ohms. The output impedance is I short BN, I get 0, 0, 0. All I see out is RC, 3K. And then the gain is apply 1 volt in. The output voltage will be minus 116 volts. So there's your gain. And here's your two-port model. Problem 4 says, let's verify that. To verify it, if this is the two-port model, think about what test you'd run on the two-port model to find each parameter. Do the same thing in the actual circuit. To find the output gain, apply 1 millivolt at the input. I should see 116 millivolts at the output. So here's the circuit. Apply 1 millivolt at the input, and what I actually see is 162 millivolts at the output. That says the gain is actually 162. To find R out, I would take the output, tie it to ground through 3K, and I'll lose half the voltage. So I'll take the output, drop this down to 3K, and see how much the voltage drops. And actually drops down to 83 millivolts, which means that the output resistance is actually 3179 ohms. To find the input resistance, apply a resistor in series. if the input resistor is 5154 ohms, I'll lose half the voltage, so I'll get half the gain out. Same thing here, make that input 5154 ohms, now measure the output voltage, and I get 51 millivolts out, meaning Rn is actually 2388. So that's kind of how you determine the two-port parameters from the circuit. Run some tests on the circuit to find each parameter, Rn, Rout, and Aout. On problem 5 and 6, it's do the same thing, but take out the capacitor across the emitter. When you take out the capacitor, what happens is that looking in, now going base to emitter, emitter is no longer tied to ground. It's now through Re. So the base resistance, Rf, goes to the emitter. Emitter goes to collector through beta IB through RC. Now find the two-port model. Looking in, what I see is R1 in parallel with R2 in parallel with this mess. This looks like a resistor that's equal to Rf plus Re times 1 plus beta. If there's a little bit of current through here, the voltage is 201 times Re times that current. So this looks like a resistor that's 201 times bigger. Putting those in parallel, it says the input impedance is 18 kilo ohms. The output impedance is still 3K. Short the input, IB is 0, beta IB is 0, I just see RC. The gain then, if I apply 1 volt in, this current is now smaller. The current is now sees a resistance of Rf plus 1 plus beta Re becomes 4.09 microamps. IC is beta times that. The output resistance is RC times IC. So the gain is now 2.885. That's what the capacitor does at the emitter. That increases the gain from 2.8 to 116. I can verify that in Circuit Lab. Take the circuit, take out the collector capacitor, apply 1 millivolt in, I make R8 0, R5 large, I'll measure the output gain. Make this 20K, the gain should drop by half, because that's the input impedance. Make this 3K, the output should drop by half. So running those three tests gives you the gain is actually 2.9. The output impedance is actually 3,000 ohms versus 3,000 calculated, and the input impedance is 17K. So that's homework set number 5.